So let's recap. But first, do you guys have any questions about layer 2? Any confusion? Any aspect that we need to brush up upon? Or do you guys want me to recap a little bit, or your pros in layer 2 now, or?
I think we have a good understanding now.
Yeah.
But if there's more for us to learn, I mean.
No, I'm not gonna give any new material. But if anyone is stumbling upon a piece, I can go back and just, like any blurry topic, whatever you guys think that. Okay. So let me give the 2 minutes recap, and we'll proceed. So basically, layer 2 deals with physically directly connected. So if you enter a classroom, you go into a single Wi-Fi router. And the proper name for it is wireless access point. So basically, all nodes in the vicinity will be talking to each other. Whereas the master node, or the central node, will be kind of coordinating. Okay. You have a distributed system where like all layer 2s together can make a decision. But most likely the thing that we deal with on a regular basis in your apartment, if you go to work, if you go to school, if you go to a cafe, you have a central authority, just like the access point, the wireless access point. So layer 2 talk. Layer 2 does not see anything beyond the physically directly connected device. So your laptop, layer 2 can see the Wi-Fi layer 2. Okay. However, it doesn't see the gateway at the school's entrance that connects the school with the ISP POP, point of presence, that we talked about. The whole purpose of the MAC layer in wired communication, wireless, cellular, it doesn't really matter. So layer 2 coordinates amongst the nodes and to tell which node can go first. Okay, without layer 2, there is no mechanism for nearby devices to talk, okay? So the language or the protocol or the protocols that layer 2 use, the physically directly connected nodes use are the layer 2 protocols, okay? Including the MAC address. So if you have two devices connected together, they're not gonna talk IP. They could, but the default mechanism is MAC address. So that's number one. We've got three big families of algorithms how layer 2 works. First one is channel partitioning. And channel partitioning, there's so many ways, by the way. But we just studied like the simplest three. Okay. The next one is when you have a central authority, like polling or token ring, or there's so many of those, by the way. But that's not really attractive solution because from architecture point of view, we have a single point of failure. From a cybersecurity point of view, if you manipulate or compromise one node, your brain can bring the whole network down. So it's not really an attractive solution. Also, from a quality of service perspective, you're just wasting too much time, querying each node. Then we moved during the lecture to the latest and greatest, which is 802.11. 802.11, that's the de facto Wi-Fi standard in the whole universe. So if you go to Mars, if you happen to go to Mars and you find the Wi-Fi there, and you want to connect your interplanetary, whatever, like laptop or something like that, most likely it's going to be Wi-Fi, okay? Most likely it will have something from like 802.11. I'm joking, guys, okay? But I just want to show how prevalent 802.11 is. So 802.11, it was based on pure random system, came in 1970s in Hawaii. And basically the first version of it was like, okay, if you have a packet, go ahead, transmit it. The keyword in the Aloha system is no priori, no prior agreement or coordination between the nodes. And that's a big thing because the whole concept, even the pure definition of layer 2 is to coordinate amongst the nodes to see who's going to access the medium first, right? But you're coming now and telling me that no priori, it was kind of weird. And the maximum efficiency was 18%, and it went downhill from 18% all the way to 0 whenever you add more users. Then as engineers and scientists think about it, it's like, what can we do to make it a little better? So they said, let's do slotted alarm. What do you mean slotted alarm? So basically add a small code in each node for two things. First, when you start the communication session, each node has to have their internal clock to sync up with the rest of the group. So you're walking into a classroom in the NAC building. Once you go in, forget about the universal clock. You will have your own clock synced up to that Wi-Fi router. I'm talking about layer 2. I'm not talking about the device clock. Okay? Advanced devices have more than one clock. And the clocks I'm talking about, these run into the order of the micro, not the milli, the microsecond level. So it has a precision. So it's like, oh, this is like 20 microseconds, 40 microseconds. So you sync up with these neighbors, and the master node or the controller node or the central authority, whatever you want to call it, it was like, yes, every 10 milliseconds or every 5 milliseconds, that's a tick. Means a time slot begins. So you're only allowed to transmit during that time slot. What was done here in the background, it's all about probability. You reduced the the opportunity for collision. You just reduce the window for collision. And again, it's not all nice and rosy, because really achieve 36%, you doubled up your efficiency from plain Aloha. But hey, once you start adding users, things will crash. And always remember, on layer 2, if you want to really measure performance, your primary indicator is number of users. That's your primary indicator. Of course, if you get like much deeper, like a PhD level research or something, you're going to look at the packet size. So probably going to have 4 users with like packet size X, 4 users with like packet size Y, or variable packet size. So you're going into more detail. But for your level, just think of the only variable that you really care about right now is number of users. Okay? And we call them KPIs, key performance indicators. So before you design a system, before you come up with an idea of a startup, like you have an idea before the implementation, before you open a business, before you do anything, between you and yourself or you and your teammates, it's like, oh, if we do this, we hit that target, that means the business is successful or the network is running well. So these are the KPIs, okay? So your KPI here, your primary KPI is efficiency. So if I say 36% success rate, that means every 100 packets get transmitted into the medium, 36 will arrive safely. And of course, you have to have like a test bed for that. So you can simulate it if you have something like OpNet or NAS. But if you want to go like really serious, you do a test bed. Test bed is like you get like equipment from eBay. You configure them. You make a small lab, okay? And you do like a Wireshark. Wireshark is a software program that captures the traffic, the packets, and actually can click on it, can decode the packet, see what's inside the packet, like everything, okay? Then, Plotted Aloha was good, but was not good enough. Then engineers was like, you know what? Plotted Aloha cannot really go mainstream technology unless he achieves 2 things. First thing is, provide us with a method to detect collision. Number 2, provide us with a method or a mechanism to recover fast from collisions. So that pushed us to CSMA. CSMA, carrier sense multiple access, employs the following. So before you transmit a packet, just listen to the medium. See if someone else is transmitting, or there's a collision or something like that. If the medium is clean and clear, again, clear, no one is transmitting. Clean means no collisions. So if the medium is clean and clear, transmit yours. So this algorithm is near perfect. However, there's a slight chance that 2 nodes simultaneously, they listen to the medium, they found it clean and clear, they transmit simultaneously, and bam, collision happened. Then came the 2 letters CD. So now we're talking about CSMA/collision detection, or CD. In collision detection, what we do, after we transmit, we don't turn off the antenna, or the antenna's controller, just to be exact. No, leave it on. Make sure the signal that you transmitted arrives safely. Of course, by measuring the amplitude and other parameters inside the medium. because the antenna can hear everything. Because the whole concept, again, for layer 2, all the nodes can hear each other. So basically, each layer 2 can cover the whole coverage area, like a classroom. So you're well hearing the signal exactly. But if a collision happens, so while you're listening, if you hear a collision, then prepare another packet and send it right away. And instead of waiting for the other node to tell you, oh, I did not receive that packet, or blah, 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 or a monitoring system tells you, like a third-party system tells you, oh, by the way, packet 228 did not arrive. No, you are proactively monitoring the medium, and you will detect any collision as it happens in real time. So that will give you the chance to quickly react and prepare a copy of the packet. And remember, our concept in the telecommunication computer networks, once you transmit a packet, you do not discard it. You keep a copy in your own buffer in case you need to retransmit. Once you get assurance from the receiver that the packet arrived safely, then you discard the packet. You free up your memory for new intake. So that's the 802.11. So one more concept. I gave you exact detail in the last 2 slides of how 802.11 works. So basically, a node listens to the medium. It's clean and clear. It will send RTS. The RTS will be received by all the nodes inside the medium. So each node will open the RTS. Basically, it's just a string of ones and zeros. So that each node will just parse these ones and zeros. So first thing they will look at the destination. Oh, is it distant to me or not? If it's distant to me and I can't really communicate, I'll send CTS clear to send. The sender will send the data, which is 1 packet normally. Then I'll send an acknowledgement. Then the 4-way handshake closes up. And that frees up the medium for other nodes to make an attempt. So those nodes who receive the RTS request to send and is not distant to them, they will take a parameter. It's called NAV, Network Allocation Vector. So the NAV is telling everyone, oh, hey, I am transmitting, and I'll be transmitting for the next 10 milliseconds. So please, please, please refrain from transmitting so collisions would not happen. That's basically what it is. Then when the medium is up for grab, 2 nodes will try to transmit at the same time. It just happened that both listen to the medium. Oh, clean and clear, transmit, bam, collision happens. Now the last element I want to talk about is the backoff generator. That's basically a small code embedded inside layer 2, and it works independently from other generators. So I run the generator. Think of it like a spinning wheel. So you have 2 people next to each other. Each one has their own spinning wheel. What are the chances that the wheel will stop at the same number in both spinning wheels? It could happen, but very slim opportunity. So what happened with the random backup generator? Node A should not transmit for the next 2 milliseconds. Good. So it will go into sleep mode. Then node D, when it ran its generator, it will tell it, oh, go sleep for 8 milliseconds. And after 8 milliseconds, wake up and attempt to retransmit again. So, of course, one node. Well, the one that will wake up faster, it will try to transmit, will listen to the medium. Oh, clean and clear, transmit, and it's good. by the time node D wakes up, it will be too late because already transmission will be happening between two other nodes. And what it's going to do is going to take the RTS and take the nav, the network allocation vector, to refrain from transmitting. Okay? So in 10-15 minutes, guys, I cap all layer 2. I want you to understand layer 2 very well. But please focus on the random. Most likely that's what I'm going to get on the way. Again, I could get anything else. So I don't want someone who's like, oh, you told us this, but you got CDMA. Well, I'm telling you now, knowing my style, most likely I'll be asking a question about the random. Okay? Questions? Okay. Everyone is good?
Yeah.
Yeah. Okay, so today I want to start talking about. So this is the last topic in the curriculum, which is TCP. So we skipped layer 3 because it's not covered under this new curriculum. But let me talk very quick about layer 3 so we don't really miss it. But I believe if you go to the grad course that Professor Dawi teaches, you will dive in detail. So layer 3 is just determines the path based on certain preference. Okay. You have so many routing algorithms, so many. And let me tell you this, 10, 15 years ago, most of the people, or the PhD students, they focused their research on routing and QoS, quality of service, how to make the communication much better, faster. And one of the ways to make it faster is to provide like intelligent routing. And actually companies did the same. And the fruits of that, we can see it now. And again, I'll go back to the example that I like to talk about every single class, the VoIP applications in our hands. They're crystal clear. And it's really mature because you call someone in the UK under 20, like under half a second, the whole thing, like once you dial it, the whole thing gets routed, registering, it's like super fast. So it's really very mature, and after 10, like, so that's what, like 10, 15 years ago. So most PhD students were like working on QoS. After that, QoS reached like a very high level of maturity, and they thought about security. Okay. So security. I talked a lot about security, so I'm not going to talk again about security. Okay. So the thing about routing, we could spend like a whole semester talking about it. Okay. So let's go ahead and talk about transport. So the relationship between routing and transport. Think of this analogy. Routing, you're sitting in your home trying to figure out how your package or how your truck can go from New York to Chicago. So you're thinking of like, oh, it can go through route X, Y, and Z, can make an exit and on that like parkway. So in routing phase, you haven't done anything. It's just all pretty much theoretical planning. But once your truck starts to move based on the routing algorithm that you ran at your home, now we're talking about the transport layer. You guys understand the analogy?
Yes.
Okay, thank you. Something also important about transport layer. This is the highest layer in terms of the electrical engineering domain. Anything above, it's the software piece. So a lot of app developers, of course, actually today he can develop an app without even knowing any code. You know, we have all these intelligent block builders that can make logic in blocks and code happens in the background. So for those like deep, like very skilled developers, at some point they will be touching upon the transport layer. Not going deep into the protocols, but at least they have to make some interaction. Not all of them, but some. Okay. So layer 2, we said your phone's layer 2 or your laptop's layer 2 only sees the directly connected node, which is the Wi-Fi router. It doesn't pretty much see anything beyond that. Okay. Come to the total opposite here. The transport layer, you're constructing a virtual end-to-end pipe. Okay. What does that mean? You are trying to log in into your email server that happens to be somewhere in Austin, Texas, and you live in New York, where your layer 2 only sees the Wi-Fi router at your home, your apartment. Layer 4 goes above that. Layer 4 does not really see the router at your home, because the router at your home maximum will have layer 3. It doesn't have layer 4. So layer 4, it goes above most of the elements in between, and it will kind of directly connect your device, your laptop, all the way to the layer 4 end for the email server in Texas. So it provides a virtual end-to-end pipe. Okay, so I can show you here. Can anyone tell me what are these devices? Come on, guys. We're almost at the end of the semester. These are layer 3 devices. Remember when I said layer 3, we call it IP, Internet, layer, so many names. So these are routers. These are layer 3 switches, which are routers. And this is probably your computer, and this is the server. So as you see, the transport layers talk to each other. I want to say bypassing, but going above all the network elements and in the network. So you're sending a traffic stream to the email server in Texas. Your Wi-Fi router does not see layer 4, the transport layer. It will just to it is just an embedded bit inside the internet or the IP layer. But in terms of opening this segment of the packet and parse it, it does not have transport protocol parser or compiler to understand what's going on. So to a router, the transport layer traffic will be just bits. Your gateway, most likely the majority of the ISP telecommunication networking elements, they still don't see what's the transport layer. So the transport layer nicely sits above all the network elements and forms somehow an assurance, like it ties your computer all the way to the server. Okay. So now, if you have your email open and your email server in Texas, and you have your social media open and your social media server in California, you will have two different transport layer pipes. Okay, so it's not per computer, it's even per application. See? So every application, so you have 10 applications, you're checking City College transcripts, you're checking your email, your video streaming on Netflix or Hulu, whatever. You have literally 10 applications. Each application will have separate transport layer virtual tunnel. So see the assurance level, it's not even coming to your device and leaves. What it does, that's the IP. So the IP comes into your device and leaves. Remember the conversation we had about the ports? You guys remember that?
Yeah.
So we said the IP is like the building number. That's your computer address. IP doesn't really go beyond that. What goes beyond the NIC card, which is the IP address, and all the way up to the application layer to see what application you're running, that's a transport layer. This is like one major or distinct feature or functionality of layer 4. It does not only go to the host level, but the application that's running on that host. Okay? Any questions, thoughts, ideas? Silence, silence, silence.
Professor, just to make clear, transport is a 4th layer or the 3rd?
I'm sorry, say that again.
The transport layer, it's a 4th or the 3rd?
Transport is the 4th.
And then was the 3rd layer? It's just
internet. So the 3rd layer, we call it internet layer, routing layer, IP layer. So it has so many names. And I purposely introduced different naming on each slide just to make you familiar with all these names.
Okay, got it.
So internet, that's layer 3. And here they combine layer 1 and 2. And application layer, we put the 3 layers together. So maybe I told you that little story. I'll tell it to you again. The naming in general, even in any course, okay? Like it could be semiconductor, robotics, integrated circuits. It doesn't really matter. Even power systems. You're going to be taught one thing. If you go to the industry, I'm talking about naming. So I'm not talking about changing knowledge or anything. Okay. So you're going to find different namings. So I just want to take that like what moment, from you. It's like, so I gave this real life example before. It happened to me actually. So I went to work with a group, and they were calling themselves the transport layer. So my mind is like, oh, so these people are engineers, highly skilled engineers. They're talking about layer 4, but they were talking about physical layer, and they're calling themselves the transport. Then at the end of a first or second meeting, it's like, guys, what do you mean transport? You're talking about physical layer. And one of them is like, oh, I know you guys, you just came, from school or something like that, from academia. Oh, and in this particular group, we call the physical layer transport layer. Can you tell them, no, that's wrong? Can you tell them, oh, change your way, change your methods because I don't like it?
No, you cannot say.
Exactly. You can't do it. You can't. You have to, you're the newcomer, you have to adapt. And these people have been doing this for the past 20 years. So you can't really tell them that's wrong. So that's why in my class, I like to introduce many names for the same thing, just to expand your horizon. So when you go hear someone is calling layer 2, XYZ layer, don't be surprised. I was like, okay, that's fine. So yeah, so internet layer here, that's the layer 3 or the IP layer. Okay. You're gonna hear people in the industry saying, oh, a layer 3 switch, an internet switch, a gateway. There's so many names for it. So let's go ahead. Sure.
So how do they determine how wide the pipe should be? I mean, does a Netflix care how thick the pipe is that goes to servers, or I'm just wondering.
What's your name?
Eric.
All right, that's a very smart question, Eric. I wasn't planning on going there, but thank you so much. I'll go there. That's very insightful, by the way. So your friend here is asking a very intelligent question. It says how big the pipe should be. So I mentioned something 10 minutes ago, but I did not really go in depth to it. I said when the software guys, the software engineers are writing the code, they may need to interact with layer 4, right? I said that, right?
Yeah.
So what happens there, and amongst many things that take place when the software guys interact with us, sometimes they dictate the size of the pipe based on the application. So the video streaming application is like, hey, layer 4. In order to give my customer the best viewing session, when you make a pipe, just make sure it's 30 megabit per second. You see? Because if you go below 10, for instance, I'm not going to be able to give her or give him the best viewing viewing experience. Of course, it's much more complicated than that because there are also some codecs and some resolution can happen on the application layer. But it has to work hand in hand with the electrical engineering layer. As opposed to something like an email, you don't really care. You don't really tell the transport layer what to dictate to dedicate. It could be anything. Could be the default, since no one really promise the email will arrive in few seconds. It could take like few minutes, and that still be accepted. Did I answer your question?
Yes, thank you.
You're welcome. Okay. So packets are coming out of the transport layer called either segments or datagrams. Okay. So first of all, there are two main protocols on layer 4. There are like a lot, but the winners are two, and recently there's one, and that will be your homework, by the way. So the main two protocols on this layer, you have the TCP and you have the UDP. And I'm sure not all of you, but I'm sure the majority of you heard about those two layers. Two protocols. TCP and UDP. They're like very, very common. So normally segments are associated with TCP. And datagrams are associated with UDP. So since you're talking about pipe end-to-end, on layer 4, what happens, multiplexing and demultiplexing. So multiplexing, first demultiplexing, if you're a sender, you have a long stream of bits coming out of the application layer. So you have to package each number of bits into a different packet. Okay. So you break up the stream of bits into packets so they can fit the MTU, maximum transfer or transmit unit. So again, each system has a maximum number of bits that can handle at any given time or handle at once. You don't want to go over that number, because if you go over that number, your system will fail. And at the receiver end, the end of this pipe will be the layer 4 protocol. It will gather these packets and we'll put them together, we'll stitch them together to form a single stream. That's how you see your movie, nice and continuous. Or at least it feels that way. You don't see like segmented packets coming, right? So let's go ahead and continue. So we talked about multiplexing. The second aspect, I don't want to say improve the service offered by network layer, but I want to say execute. I'm not going to correct it here on the slide, but I want you to write this note. It doesn't really improve the service offered. It does, because, like the IP will leave the packet at the door of the computer. But the layer 4 will take the packet from the entrance of the computer all the way to the application. But also I want to add, it executes on the route that's selected by the IP layer. Okay, network layer, IP layer, internet layer, layer 3, they're all the same thing. Okay. So now we understand why we say improve and execute.
Yeah.
Okay. So we talked about this. So here the multiplexing and demultiplexing and separate pipes are related to ports, directly related to ports. So that's why I talked about ports at the few classes ago. Because that's the only way. So basically the end of the transport layer tunnel will be ports. Port number on your device and the port number on the, whereas the IP address will just stop at the network address card on your computer. It doesn't know which application to go to. Okay. So we're ahead here. We talked about port numbers. So one aspect, if you're going to the business of studying the protocol, modify them or come up with a new protocol, you have to understand the packet architecture. The packet is just zeros and ones, but it has architecture. It has a very strict architecture. And the architecture is determined by the position of the bit. Okay? So for instance, the first 2 bits or 10 bits will determine the protocol name and type and version. The following 2 bits or 10 bits or 20 bits, it will determine the port number or the IP number. Like each number of bits based on the location inside the packet will have valuable information. And that's how they get parsed. So basically the parser on layer 4 will know, yes, oh, Joseph is talking to me via TCP version 20. There's no version 20, I'm just saying that for explanation. Okay, so Joseph is going to talk to me on layer 4 TCP version 20. Good. So the node will prepare a parser that can understand this particular protocol and this particular version. Once I send a packet, yes, I'll look up in the dictionary or I'll look up a book or something. It doesn't look up, of course, but it's like everything is automatic. But I'm just giving an analogy here. Oh, yeah, so layer 4, version 20, the first 80 bits represent the port number. So I'll parse the 80 bits, ones and zeros, and come up with port number 63,000. The next 20 bits will tell me the class of service. What is the class of service? Oh yeah, because if you're a first responder, phone or laptop, we're going to insert something in your computer or device to put some bits to tell us, oh, that you are, your call is very important because you're a first responder, and we should treat it with care, and we should prioritize it over other people's communication. The next 100 bits, will represent maybe a highly paying customer. So when you go get your internet, right? Is there one plan or several plans?
Several plans.
There's several plans, right? There's never one plan. At least from what I've seen, there are always several plans. You know, and every time it's like, oh, do you want to upgrade? Do you want to upgrade? So you have the regular people service like us, you know, like residential. Then you can go up to small businesses, then mid-sized businesses, then big business. And of course, though, every time you go up, you have to pay much more. And of course, you're going to get more service, but you'll have to pay much more. So all this information is embedded inside the packet. So how the parser will know which service that packet belongs to? By looking into a specific location inside the bits, inside the packet. So for this one, for instance, just very generic. So the 16 bits, first 16 bits will tell you the port number of the source. Next 16 bits will show you the destination of the port number. Other header file fields, like could be IP, could be a special handling, class of service, could be anything. And here, that's your data. That's your actual data. So if you're watching a movie, the application layer will extract these bits, and that will contribute directly to your viewing experience. So these overhead bits do not really contribute directly to your viewing experience. So good engineers try to make this as much as small as possible. Also, when engineers write the standard to construct a packet, they will have to leave like few empty fields just for future use. Okay. Questions? So when we talked about ports or port numbers, we talked about sockets, right? So socket is a combination of IP address and port number. So I'll move, like fast forward, I'll tell you what's different between UDP and TCP. UDP is very unreliable protocol that does not wait for acknowledgement. UDP, they call it in the industry, send and pray. So UDP, you just send. You don't care if it's going to arrive or not. You just send. Questions?
Oh, just laughing at the name. It's funny. It's like the way you
Yeah,
say
it is. I mean, it is. Yeah. No, that's for real. It's called send and pray. TCP is very tight. It's tightly controlled. So I need to get an acknowledgement for every single packet I transmit.
So with UDP, you can't have a retransmission of lost data? Okay.
There's no such mechanism.
Oh, okay.
There's no such mechanism. If you want to do that, you track your lost packets, you use TCP. You configure your layer 4 on TCP.
So what's the main benefit of using UDP over TCP?
I'll tell you what it is.
Okay.
So when you send zillion packets to watch a movie, do you really care if few packets get lost?
Not really.
Not really, right? If you're playing a very rich, like media-rich game with your friend, like super rich, like the colors are very bright, it's like how do you say that?
High graphics.
Or like hyper reality. You know, extremely high definition. So they're sending you gazillion packets per second. contribute to that nice user experience. So if you lose 100, do you think your eyes will notice?
Probably not.
It's not going to notice. So, but if you go like 40% loss rate or 30%, then your eyes will notice. Then we're in trouble. But UDP is made for, if I send you 2,000 packets, but if I lose 20 packets in the process, I don't really care, then use UDP. But let me ask you a question. If you want to deposit $10,000 in your bank account, and the whole transaction will take 100 packets, can you afford losing 5 packets in the process?
Definitely not.
Definitely not, because you could be losing some of the digits in your bank account. You know? So in this case, you have to use TCP. Not really you have to, because I'm going to contradict that in a minute, like later on in a few slides. But for now, I want you to understand that. And I'll show you how things are, like in technology, evolve over time.
So Professor, who decides if it's either UDP socket or TCP socket?
It's you, the engineer.
Okay, the engineer decides it.
Yes.
Not the end user, because they don't have any access.
No. The end user doesn't do much. So again, remember when I told you when you write the application?
Yeah.
The software developer, they talk to the TCP, the electrical engineers, and they agree on a model. So when you download an app for Netflix or Hulu or banking or something, the app is just software. But it makes connection to the transport layer, and inside the app, it tells it exactly what protocol it wants.
Yep, that makes sense.
So yes, if you work in such an environment, you will have to talk to the engineers. You know what? Let's do this. Let's do that. Okay, can we afford losing 5 packets at 1,000 if we're doing banking? The answer, maybe the application guy will like, oh yeah, we can do that because we have certain systems. Or it can say, you know what, you're crazy. You can't, because now we're gonna deposit the money in someone else's account. So that's part of the conversation that will happen in real life. Okay.
So an application can have multiple sockets. It can have UTP and TCP, right? Like
at the same time, no. At the same time, no. It's either or.
Oh, either or.
Because the port numbers is like apartment numbers, okay? So I'm sending you a package. It's either going to apartment 6 or apartment 9. You know?
But inside Netflix, we have like login functionality, we have payments, and we have a lot of other secured features that we don't want to lose. So
each one could be on different ports. I don't know like how things happen in the background.
Yeah.
But if I were the designer, I would make streaming on a certain port, provisioning, because paying money part of provisioning. Remember the provisioning flow?
Yes.
That we talked about?
Yeah.
So I would make that provisioning, because you put your credit card and it gets like deducted monthly or something.
Yep,
I would use different port numbers for that. So if okay. Rule of thumb, guys, you never want to mix up the ports. You have 64 minus 1,000, like 63,000 ports. Try to make a port for each functionality. Because let me tell you this. You're watching the movie, high def, in the middle of it, like, oh, I need to update my email address. Do you think it's wise while you're watching the movie that the app will let you use the same port to update your credit card or something with your phone address or email address, whatever?
No.
It's not wise. You want to use different ports. Again, I don't know how these apps are constructed. I'm not privy to such information. But if I were the designer, I would make different ports for each functionality. Matter of fact, I'll make like outgoing traffic on a single port and incoming traffic. So if you're paying credit card like the provisioning flow, I would make the app on your phone, ongoing traffic from your phone to the server on port like say 7,000, but the acknowledgement that your payment is accepted or your email is updated on port 7001 or 7002. See, when you separate the traffic, it's good for everyone. Good for security. It's good for network pipe separation. So by merely looking at your activity on port 7001, it's like, hey, we send them an acknowledgement right here. You see? You guys see what I'm saying, or you're not visualizing?
Yeah, it makes sense.
Okay, thank you. And thank you for asking. Yes, so basically, the engineer will be coordinating with the app to which port you will choose. So in 2008, 2009, I was working with this consultant that we put about 13,000 traffic controllers in New York City. I was one of the engineers that did that. And all of them, they communicate to a single server in Queens, hosted by the New York City DOT. Initially, we turned on TCP. Guess what happened? The network choked on acknowledgements. The network literally choked. So the traffic control will give the status to the central server. Hey, I'm up, I'm running red, I'm running green. So all these updates. So the network could not really be up and running. And you know what? Our chief engineer back then, he had to turn it to UDP. He said, like, you know what? He was like the chief architect of the system. He's like, turn it to UDP, and it's okay if I lose an update from a traffic controller for like 2 minutes. You know, nothing will happen really. You know, because you're not monitoring all the 13,000 anyway, because they have like a fail-safe mechanism. Even because they're communicating just to relay the status, it's not controlled by central. So they have their own brain. So even if they're not telling you as in central their status, they're 100% running safely in the field. You see? So it's not impacting safety. It's not impacting anything. If there's an alarm, it will override the system and will come to you via polling or something. Not polling, but trap, something called trap. So if something wrong, you will know it right away. But just for the mere communication, make it UDP. You know, the system really choked for TCP. So again, you as an engineer, you have to understand the difference. You have to understand your application, and you have to know the consequences. If you don't get the update, if you don't get the communication, is it okay or not? And that's what the chief engineer did. It's like, you know what? Nothing will happen because each local traffic controller has a safety card. So no matter what happens, it will not violate that card setting, and it will run green when it's green and run red when it's red. See, so so what I'm teaching you guys is not something, you know, like just a protocol like on paper and stuff like that. No, these are actually stuff that if you work with some application, you have to make a decision. Of course, you're going to be a junior engineer once you graduate, but it's good when you sit with these senior engineers, you understand, you know. And matter of fact, you may add some insight based on the things I'm teaching. So let me stop here today. Any questions? So what I told you about the homework. So I'm not going to give it today, but I'll tell you what it is. So the vast majority of layer 4 protocols are TCP and UDP. But there's something called QUIC, and it just mixes UDP and TCP together. But don't do the homework yet. But I'll go quickly over QUIC, and maybe next class or class after, I'll ask you to send me like just a paragraph about QUIC, because it's gaining like a lot of traction. Okay?
Okay.
Good? Questions?
Michał,
Okay.
coś odezwać?
Me too.
Odezwać chcesz?
Thank you, Professor.
Take care, Professor.
Chodź, bo oni się wylogowują. Oni się wylogowują. No, chodź. Weź, wyloguj się. Okay, that's good.